Good day, dear students and teachers who are watching my video lesson. Today our lesson is about data representation. The lesson is presented by me, teacher of Nazarbayev Intellectual School of Taldykorgan, Еркинова А Е. Let's look at this word cloud and see if there are any words that are familiar to us. Yeah, there are some familiar words like a binary, decimal, column, number. The main word is number. We'll look at the different ways how we can represent one number in different systems. Let's look at the binary system. There are only two ways we can have a binary digit. It is like an on and off for a light bulb, or 1 or 0. Counting in a binary number system is quite simple. It is like in a decimal. We start counting at 0, then goes 1, but then there is no symbol for 2. What do we do instead of 2 in decimal? How do we count decimal? We have to remember that first. We start at 0, then count from 1 to 8, and then the highest digit is 9 in decimal, and after 9 we start back at 0 again, but add 1 on the left. So in binary the counting system is quite simple and like in decimal. Let's start at the beginning. Start at 0, then it goes 1. Now start back at 0 again, but add 1 on the left. And one more. But now what? What will go after 2 ones? It will go the same, and instead of 2 ones there will be 2 zeros and another 1 on the left. Let's look at binary addition. We know how to represent numbers now, and we have to remember how to add numbers in binary that are only ones and zeros. 1-bit binary addition works on the same principle as the decimal numbers. When 0 plus 0 gives us 0, 0 plus 1 gives us 1, 1 plus 0 gives us 1. It's not so difficult, it's so simple. But after that, we came to 1 plus 1, which carries us into the next column. In binary, any digit higher than 1 puts us a column to the left. It means that 1 plus 1 gives us the result 1, 0, like a 10 in decimal. The process is the same for multiple-bit binary numbers. Let's look at this example. We have two binary numbers. First one is 1010, the second one is 1111. If we add these two numbers, what we'll have as the result? The most right digit of the first number, 0, added to 1, the most right digit of the second number, will give us 1. The same for the second one, but the second digits, 1 and 1, gives us 1, 0, as you remember. We write only 0, and 1 we will just put in our memory. And the same process as in decimal, it goes further, and we will have the result 1, 1, 0, 0, 1. Try a few examples of binary addition. I will give you a couple of minutes just to try these examples by yourselves. But when you're doing these examples, you have to remember that 0 plus 0 gives us 0, 1 plus 0 gives us 1, 0 plus 1 gives us 1, but 1 plus 1 gives us 1 and 0, like a 10 in decimal. It means that we write 0 in the same column as 2 ones and add another 1 to the right column. And let's just check your answers. The answer of the first example is 1101. The answer for the second one is 1100, and the third one is 1110. And if you have the same results, well done. Let's look at binary multiplication. Multiplication in the binary system works the same way as in the decimal system. 1 multiplied by 1 gives us 1, 1 multiplied by 0 gives us 0, and 0 multiplied by 1 gives us 0. Here is an example. Let's look at the number 101 multiplied by 1, 1. First we take the most right digit of the second number and multiply it by the first number whole. It gives us 101, the same with the second digit, but also we add 0 at the end, and it will give us 1010, and the addition of these two products will give us 1111. Try a few examples of binary multiplication. Sorry for the errors on the PowerPoint, but here you have to multiply these two numbers between each other. First example is 1011 multiplied by 110. The second one is 101 multiplied by 11, and the third one is the easiest, 1101 multiplied by 100. If you have finished, you can just check your answers, check your result with the answer. And if you have these answers, well done, you're good at counting. So, how do we know what binary number represents the exact decimal number? We know that binary represents in ones and zeros. We know how to add and multiply these numbers, but how do we know which of these ones and zeros gives us the exact decimal number? In the decimal system, numbers are organized into columns: hundreds, tens, ones. So the number 563 is 5 hundreds plus 6 tens plus 7 ones. In power of 10, it will look like below. 5 multiplied by 10 in power of 2 plus 6 multiplied by 10 in power of 1 plus 7 multiplied by 10 in power of 0. The binary system works under the exact same principles as the decimal system, only it operates in base 2 rather than base 10. In other words, instead of columns being 10 in power of 2, 10 in power of 1, and 10 in power of 0, they are 2 in power of 2, 2 in power of 1, and 2 in power of 0. Let's watch a video tutorial.
Digital computers use electronic circuits called flip-flops to represent numbers. Each flip-flop can store a single bit which can represent either a 0 or a 1. Multiple bits can be combined to represent a base 2 or binary number. In the binary number system, 0 and 1 are the only two numeric symbols. Since binary is base 2, each column multiplier is 2 times the multiplier of the previous digit. And just like decimal or octal numbers, the value of a binary number is the sum of all its digits times their multipliers. Since the digits are either 1 or 0, the calculation is simple. We just add the multipliers of all the columns which contain ones. For example, the binary number 11010 represents 116 plus 18 plus 12, which is equal to 26.
Historically, encryption was widely used only by the military. But with the advent of the internet, almost everybody needs it. Encryption is a way to ensure privacy by changing your online messages into sort of a secret code. Most web browsers automatically encrypt text when connecting to a secure server. That is, a web address beginning with HTTPS. The messages or files are scrambled as they travel in between computers, but then the message is decrypted when it arrives at its destination. So if you bought something online, the sensitive information like your address, credit card, or phone number is usually encrypted. But not all the information exchanged online is encrypted, and not all encryption methods are created equal. Like 64-bit encryption used to be all the rage, but nowadays 120-bit is the standard. And even that will surely change and get better as time goes on. And it should. Unencrypted internet exchanges are not only accessible by virtually anyone, but they can be available for years, and possibly on servers that could change ownership or become compromised eventually. So it might sound mysterious, but encryption is your friend. I'm Holly for Tech News Daily.
As you've seen in the video, it means the number 10111 in binary system represents 1 multiplied by 2 in power of 4 plus 0 multiplied by 2 in power of 3 plus 1 multiplied by 2 in power of 2 plus 1 multiplied by 2 in power of 1 and plus 1 multiplied by 2 in power of 0, which gives us a decimal number 16 plus 0 plus 4 plus 2 plus 1. As a result, we have 23. Now try to convert these binary numbers to the decimal number system. You should remember that the counting of the powers will go from the right side to the left, and the most right digit will be multiplied by 2 in power of 0, and the second one multiplied by 2 in power of 1, and etc. After this, all the products have to be summed together. If you have finished trying this, now just look at the results. Here are the results. The first number was 15 in decimal system, the second number was 42 in decimal, and the third one is just 6. Now let's look at trees in data representation. Trees, especially in the form of binary search tree, are useful for organizing data, which makes it quicker to find specific elements. Trees are dynamic data types, and it is very useful to save data in this type in order to use efficiently the memory of the computer. And now let's look at root trees. A rooted tree is an abstract data type consisting of nodes arranged in a hierarchical fashion with the root node at the top. Every other node is a descendant of the root. Nodes are linked by branches. A node that has a parent and itself is a parent of one or more nodes is known as an internal node. A node that has a parent node but is not a parent of other nodes is known as a leaf or terminal node. Let's look at this diagram and just label these three main parts. Here we see that the parent node is called root, and we see the internal node that is called also just node. We see the branches coming out from roots or nodes, and the leaf or terminal node that have no nodes coming out from them. What is binary tree? In a binary tree, there are never more than 2 branches descending from a node. A binary tree is either empty or is partitioned into 3 subsets. The first subset contains a single element called the root of the tree. We can see it in the diagram below, that in the middle there is a root. The other 2 subsets are themselves binary trees called the left and right subtrees of the original tree. Just look at the labels of this tree. We can see where is the left subtree, root, and right subtree. Ordered binary trees. It is possible using a binary tree to sort an unordered list of items into a particular order. For example, consider the following unordered list of integers, like 30, 20, 41, 25, 37, 17, 56. An ordered binary tree is created as follows. Starting from the leftmost integer in the list, the root node is created first. As you see in the picture on the right, the number 30 will be our root. The next integer is taken and placed in the left subtree if it is numerically less than the root node integer or equal, or in the right subtree if it is numerically greater. We take 20 and we look at this. We know that 20 is less than 30, therefore it goes to the left subtree. The next integer is numerically greater than the root node integer and so goes into the right subtree. Therefore 41 will be in our right subtree. The next integer is numerically less than the root node integer but greater than the integer at the root of the left subtree. So it is placed to the right of this node. The same principle for all other integers. Now just look at our binary tree that as a result of the whole algorithm. The remainder of the list is processed to produce the finished ordered binary tree by visiting the nodes of this tree in left to right, bottom to top order. An ordered equivalent of the original list is produced. This ordered list has placed integers in ascending numerical order as follows. You can see that it is now ordered, and starting from the list 1, 17, then it goes 20, 25, 30, 37, 41, and 56. Therefore, it is called binary tree, ordered binary tree. Now, let's try to turn this list of integers into an ordered binary tree. Here are given some integers like 12, 9, 11, 6, 5, 15, 7, 14, and 20. Here you have to remember that in ordered binary tree, the first integer in the list will go as a root and will stay in the middle. The next one will be compared with the root one, and if it is less or equal, it goes to the left subtree, and if it is greater, it will go to right subtree. And each next element will be compared first with root and then with its nodes, and it will take its own place. If you have finished, now just look at the result of this. You have to have the tree like this. And please remember that in binary tree, each node have only 2 branches going out from this node. Here your home task. You have to try convert next given binary numbers into decimal number system and put into binary tree in correct order. Just to summarize all the lesson, Here are given only just some binary numbers and also some operations to multiply, add numbers in binary, and you have to, after these operations, convert it into decimal and the result put into the ordered binary tree. Just for fun, there is a joke that there are 10 kinds of people in the world, those who understand binary numbers and those who don't. If you understand that. Let's try to do some feedback. Can you answer the questions? Today I learned. What do you learn today? That binary numbers consist of only 2 digits, 0 and 1. How to add binary numbers and how to multiply them. What was interesting for you? I hope that everything was interesting for you. I would like to know more about. If you have any questions, you can ask anytime. What was difficult for you and what would be better to add or change in this lesson. I think your feedback will be very helpful for me. Here are some resources, some links to the resources that I've used. And thank you for your attention.